Applications of Integration, Volume by Slicing, Part 1. Suppose we would like to find the volume of this solid. Imagine slicing the solid as if it were a loaf of bread. Each slice of bread is called a cross section. Now if you take one of those slices and turn it towards you, then what you're looking at is what we call the area of the cross section. Notice that as x moves from A to B, the area of the cross section changes. So we say that the area of the cross section is a function of x. So each cross section has area A of x, and it's going to have width dx. Think of dx as a very thin or a very small number. These are very thin slices of bread. Think of it more as maybe sheets of paper. So what is the width of a sheet of paper if you were to turn it? It's very, very thin, isn't it? So if you take the width times the area, then each cross section has a volume of A of x times the width dx. If you were to add up all of these pieces of bread or all of these slices of paper, you would get the total volume of the solid. We now consider a specific type of solid known as a solid of revolution. Suppose we revolve the region R around the x-axis. Think about what that would look like. As R revolves once around the axes, it sweeps out a three-dimensional solid of revolution. The goal is to find the volume of this solid. If we slice the solid, then we can see that each cross section is a disk. So remind yourself, what is the area of a circle? The width of each disk is dx. Think of again a very small number dx, infinitesimally small. So very, very thin. These disks are very, very thin. The width of the disk is dx, and the face of the disk is a circle with area pi r squared, so radius squared. Now what's the radius of the disk? The radius of the disk is f of x. So that's where you get the pi f of x quantity squared. Again, if you were to take that area of the cross section and multiply it by the width of the cross section dx, you get the volume of one disk. Add up all your slices and you have the total volume of revolution. Let's do an example. Let R be the region bounded by the curve bounded by the curve f of x equals x plus 1 quantity squared, so that's your function. It's also bounded by the x-axis and the lines x equals 0 and x equals 2. Before we proceed, let's find the region R. First of all, what does the curve look like? What does f of x look like? So there's your f of x. And your x-axis, it's also bounded by your x-axis. And it's bounded by the line x equals 0, which is the y-axis. And it's also bounded by x equals 2. And so you can see that your region is bounded by these four things, is the area in blue. And suppose we revolve this region about the x-axis. What would be the volume of the solid of revolution? Well, we have the volume of each disk. And ask yourself, what is f of x? Then simplify the expression. You have something squared, squared again, and so it's to the fourth power. That's the volume of one disk. So the volume of the entire solid is just adding all these disks up. The rest is calculus. In order to integrate this, we're going to use substitution. Let u equal x plus 1. What is du? So du would be the derivative of this times dx. So du, the derivative of x plus 1 is just 1, so it's just 1 dx. Now if x equals 0, remember u is 1 more than whatever x is. So if x equals 0, u would have to be 1. And if x equals 2, u would have to be 3. Do all your substitutions. Instead of a bound from 0 to 2, we have a bound from 1 to 3. Instead of x plus 1, we have u. Instead of dx, we have du. Once you do all that work, it's just a matter of integrating and evaluating. So when you integrate, you get u to the fifth over 5. And then when you evaluate, you're evaluating from 1 to 3. When you evaluate, you get 252 divided by 5 times pi. And those are cubic units. Take care, and I'll see you in part 2.